Welcome back, dear students, to Math 204, Tutorial 5. In this tutorial, we are going to discuss the subspaces set, the linear dependency and independency, and the basis and dimension. So in the last time, we have discussed the span set. And remember that we have said that the span set got a definition. So once we see a span set is mentioned, what comes in our mind is the set of all possible linear combinations. And we said that we can have two vectors like 1 and 0, vectors 0 and 1. And if you are discussing the span set of these two vectors, it means that we need all possible linear combinations. And to mention it in general format, it means that we have any constant times this vector plus any constant times that vector. What happens is that for every corresponding value of a and b, if a and b both belong to the set of all real numbers, for every corresponding value of a and b, we will have a vector. It seems that a, or that vector, the first one, 1 and 0, is filtering the x coordinate, and the other vector is filtering the y coordinate, setting it by b, which can be any number in the real numbers. So the span of such two vectors will form the two-dimension space, or the R2, all the points of two coordinates. So if we imagine the x and y coordinates, this is the two dimensions geometrically. All the points that lies in this coordinate are existing in that R2. All points in each corners, including the 0, of course. So that was the span set that we discussed last time. And this is if we are spanning here two vectors. So this is the form, how it is. It will give us a solution. So if we equate this by 0, it will be the 0 vector. We can write this form or this system matrix format or matrix form, and we can solve it, and we will find a solution, and not only one solution possible for a and b, but infinite number of solutions. And this is what will construct this set. The span set included how many number of vectors do you think? If we said that a and b belongs to the set of all real numbers, so they can be any value, and therefore it included infinite number of elements that can be vectors or matrices or polynomials. These are mainly the elements that the linear algebra is interested in. So let's now move to the subspaces, and it's a new form of a set. So the subspace is a sub of a space. If we thought about the subspace, we will say that it's a subset. It's a subset of a vector space. A vector space which we can call it Rn. I want to grab your attention that the name vector space doesn't imply that the elements inside the space or that set are vectors. Let me say it in other words. We have something called a vector space, which is a set of infinite elements. For example, it includes the 1 and 2, the 2 and 1, and all the infinite elements, all combinations that can come to our minds. So it's an infinite set, okay, that includes all types of vectors. If we mention here the vector that belongs to the dimension of 2 dimension, then we are talking about R2. This is one of the basic vector spaces. Also, we have mentioned the M, the set of matrices. So we might be talking about the matrices which is of size 2 by 2, and in this case we mention all of the matrices that have dimension 2 and 2. These are two examples, and then all of the other possibilities, all of the other possible combinations are included. This is one of the standard vector spaces. R2 is another standard vector space. If we need to get only some elements of this set or that one or any other space, we will take a subset. If we took part of the elements, it means that we got a subset. This subset is going to be called or labeled subspace if three conditions are implying for the subset. Let's call the subset W, and W here, W is a subset of V. V is a vector space. Okay, it's a set of infinite number of elements. These elements can be vectors, can be matrices, can be polynomials, but it is called vector space. Okay, this is how we call it. And we have a W, which is a subset of this infinite set. This W can be called a subspace if it's a non-empty set, which means that the zero is included in W. The zero belongs to the W, of course, the zero vector, or according to the dimension of W. Also, if we have two elements that are inside this W set, included in the set W, their addition also has to be inside the W. And this property is called additive closure, or we might call it closed under addition. So if the addition of every two elements in that subset exists in that subset, it's called closed under addition. If the scalar multiplication of every vector or every element in this set exists inside the set, so it's closed under scalar multiplication. What we are going to do in the problems is to test these three elements. Okay, let's remove that part of our discussion here. I will just keep that the subspace is a subset of a vector space, which means it's part of it, and we knew now examples for the vector spaces that it can be the set of R2 that includes all the points in the two dimensions, or we can see them as vectors of two dimension, or R3, which is all possible vectors that exist in R3. This is its vector space, or the matrices, the elements. Also, like here, it's all of the matrices that are of size 2 by 2. So now we have an idea about the vector space, and we will not discuss it further. We can call this vector space Rn because it might belong to any dimension n. Now, the subspace which is of our concern is part of this vector space, is a subset taken from that vector space, whatever it is. And because it's a subset, we cannot call it a subspace except if these three conditions apply. Let's apply this for part exercise 1, part A, U0. Here, the problem. So here we have part A. Here, U0. U0 is described as lambda times 1 and 0, such that lambda belongs to R. Remember the set builder notation? We said that at the beginning we have the shape of the vector, and then this bar, and after that the condition applied for the elements that should exist in that set. This U0 is subset of R2. It includes some elements that exist in R2. And we have just mentioned that R2 means that we mean all the vectors that lies in the two dimensions. We can say it vector of two elements or the coordinate of the points in the xy plane. all of the points, including the 0 and all the points in every corner. So now lambda times 1 and 0, we need to apply the first condition of non-empty set. So we test the 0. Does the 0 exist in that U node? This is what we are seeking. Is the 0 vector exist? U node is of vectors of 2 elements, right, of R2. So it means that this 0 here is the 0 vector of 0 and 0. Does the vector 0, 0 belongs to U node? Let's see a value that can make it belongs to it. Setting lambda by 0, so we will say that at lambda equals 0, at this lambda equals 0, the vector will be what? The vector will be 0 and 0, right? Because we apply the scalar multiplication. If lambda is 0, and we will distribute 0 times 1 and 0 times 0, so we will get the 0 vector, and in this case 0 vector will belong to U node. If we expanded this set, it will include the vector 0, 0. So now let's move to condition number 2. We will repeat this several times. In condition number 2, we need to decide whether the sum of 2 vectors that belong to U node, does they belong to U node as well or not? Which means that we need 2 elements that are of that shape and applying this condition. So let's take X, let's keep X as, for example, lambda 1, we look to the shape, take the character and give it sub 1. This is the easiest way. Of course, there is many others, but let's keep it that way. So we will distribute the lambda 1 and we get lambda 1 and 0. This is for X. The other component Y, which will be lambda 2, because this is the second element, again multiplied by 1 and 0. I got this from the shape here that was described in the set builder notation, applying the scalar multiplication. So it will be lambda 2 and 0. These X and Y, X and Y, both belong to lambda node. And when I say that X belongs to lambda node, it means that X got the shape of the vectors in lambda node, and also the condition is applied. So it means that that lambda 1, like that lambda, belongs to the set of all real numbers. The same implies for Y. So here Y also belongs to U node, right? Like X. Now we have the 2 elements, so let's test their addition. Let's add X plus Y, and of course we add every 2 corresponding elements. So I will add lambda 1 plus lambda 2 and 0 plus 0. We need to set it in the shape of that vector. Now we need to test whether this sum belongs to U node or not. This is what we need to test. So let's reshape it. Let's take lambda 1 plus lambda 2 as a common factor outside, and then we will be left with 1 and 0. Now it's in the shape, right? What about lambda 1 plus lambda 2? Does it belong to the set of all real numbers? Let's recall that we said that X belongs to U node, right? And Y also belongs to Y node, which means that lambda 1 and lambda 2 consequently were belonging to the set of all real numbers. And the sum of 2 real numbers will get a real number as well. Therefore, this addition or this resultant does belong to U node. I want you to continue, please, and don't panic. Continue till the end, and we will repeat several problems. Okay, the third condition is testing the scalar multiplication, whether C times the vector X does belong to U node or not. This is what we are testing here. Of course, C, as we say also always, that C belongs to the set of all real numbers, right? We have to mention everything. Okay, now we have mentioned X, that it's of that shape and it belongs to U node. So that character in X belongs to the set of real numbers, because if it belongs to U node, it implies what is in U node. And here we have introduced C, so I have to define what is C. C belongs to a set of all real numbers. Okay, then it's a scalar. Now multiplying a scalar by a vector, This is so simple that it was C times the vector x, C times the vector x, which is lambda 1 and 0. So it will be equal to C times lambda 1. I will distribute the C over the two components. It will look like this. Now I need to test whether the scalar multiplication does belong to U node as well or not. So it will look like the set builder notation of U node. Taken the C and the lambda 1 as a common factor, I will be left with 1 and 0. And this shape is the same shape of the vectors that was described in U node, right? And C, we have just mentioned that it belongs to the set of all real numbers. Fine. Lambda 1 also, because we said that x belongs to U node, and U node got that coefficient, that character was belonging to all real numbers. So the product of two real numbers is a real number. And therefore, this vector, this product will exist in U node. So what we are searching for is true. Now we have tested the three conditions. The 0 vector, it does exist. Also the addition is closed. So this U node is closed under addition. So it was non-empty. It holds the 0 vector. It was closed under addition. And by the third condition also, it was closed under scalar multiplication. The three conditions exist. Therefore, we can directly conclude that hence, U node is a subspace. So it's not only a subset, no, it's a subspace as well. Okay, let's move to exercise 2. Here, exercise 2 give us, again, a set builder notation with different description. Now, it describes in the first part the shape of the elements inside this U2. U2 is an infinite set of elements. It's a set which includes infinite number of elements. What's the shape of these elements? Now the problem indicates that U2 elements are vectors that belongs to R3. Very good. Belongs to R3 means that there is 3 components in each. Right? We might call them X1, Y1, Z1. This is a component or an element that we can call it X that belongs to R3. Right? Because it's composed of 3 components. Very well. What's the condition? The condition is that its norm is less than or equal 1. Remember the norm? The norm of such a vector, will be equal to the square root and the sum. The sum, please don't forget it's the sum. This is the rule of the squares. Sum of squares, squared values. Right? Now, what are the values? This is the easiest part. What are the values that we will fill in here? Of course, they are the elements. We don't have except the elements. So it's a sum of squares of the elements of the vector x1, y1, and z1. That was the norm, that it's indicated to be less than or equal 1. Fine. And this set is a subset of R3. By the way, just to note, if we need to describe the set R3, R3 includes all the vectors that are of 3 elements, of 3 entities, of 3 tuples, of 3 components. So the vector 1, 0, 0 is there. All the vectors that can come to your mind now exist in R3. It's an infinite number of elements inside R3. It's a vector space. Okay? If we need to describe it, because it's of infinite number, not finite, so if we need to describe it, we use this set builder notation. So we will denote the shape. We will say that this is the shape of the vectors in that set. And then, do we have any restriction in the elements? The elements can be of any combination, right? Because we are talking about the space itself of R3. So we say that X, Y, and Z the three elements does belong to the set of Euler numbers, which means that every element can be any number. So x, y, z can be of any component. This is just for our notice to make sure that of our understanding. Now let's get back to our problem, that it indicates that we have U2. U2 that we are speaking about now is only a subset of R3. So it's including some of the elements that are in R3. Only some subset. We need now to test whether this subset is a subspace or not. Is this subset a subspace or not? This is what we are testing. That was from the previous problem, this part. Okay. So here we need to test whether this is a subspace or not. This U2. Very good. Let's test the first condition about the non-empty, whether this U2 is non-empty or not. It includes the zero vector or not. And we will take the zero vector, which is something like this, and try to, it's of that shape, fine. Now try to apply this condition. So the norm of the zero vector will be the square root of 0 squared plus 0 squared plus 0 squared, right? And this is equal to 0. Is it less than or equal 1? This condition that's stated here? Yes. Therefore, then the zero does belong, the zero vector does belong to the U2. And U2 is non-empty. Okay? Number 2, we need to discuss the addition. Okay, we have here x, which is one element of U2. Let's say that this x belongs to the set U2. I need another element, so let's call it y, and in this case I will take the characters with a different sub. This is the easiest way. You might call it a, b, c, or mt, whatever. These are only simples of dummy variables, but we just need to be organized in order not to be so loose. So y belongs to U2, and by mentioning that this y belongs to U2, it means that the norm of this vector is less than or equal 1. It means that it's of the shape R3, and this condition is applied or is true and fulfilled. All this we have said when we say that y belongs to U2. We have said this in consequence. Okay? Now we need the addition of the two elements, which are x plus y. These are the two elements that belongs to U2. Their addition will be x1 plus x2. We add every two corresponding elements. y1 plus y2. The third component is z1 plus z2. Right? And this is the sum. Now, does this norm, now we have stated the shape, does this condition is applied? Let's take the norm of the vector x plus y. It will be the square root of the first element, which is now x1 plus x2, all squared, plus y1 plus y2, all squared, plus z1 plus z2, all squared, right? This is the norm. Now the question, does this norm is less than or equal 1? Does that norm of x, when it's less than or equal 1, and the norm of y, of these elements, when it's less than 1, does this implies that the addition or that norm is less than or equal 1 as well? Let's take a numeric example, because some of you can see it, that you will say the answer, or she will say the answer directly, if it's yes or no, and others need numeric example to view it. Let's take simple numeric example. If this x was 0, 1, 1, for example, any simple vector that applies the condition. So if we consider the vector 0, 0, 1, getting its norm, it's 0 squared plus 0 squared plus 1 squared. Under the root, it will be 1. So it is less than or equal 1, right? Let's take another very simple also. vector here starting with 1, 0, and 0. The norm here is 1 as well. Let's now test the addition. Tell me about the addition. x1 is 0 and x2 is 1. y1 is 0 and y2 is 0. z1 is 1 and z2 is 0. Now adding these two elements and take the square, you will get what? Yes, without continuing, we know that it's the square root of 2. Therefore, it's not less than or equal 1. Therefore, it does not belong to the set U2. So the sum, that sum of the two elements that were belonging to U2, their sum doesn't belong to U2 because the condition is not applied. Therefore, I will conclude the following. We have to mention the conclusion that therefore U node, or here it's U2, is not closed under addition, okay, and hence U2 is a subspace or not? Of course is not subspace, is not a subspace at that time. Okay, let's take another example from the worksheet. Let's take here, I want to take number E first, and then we will get number T. So here we have U4 in E, and this is the shape of the vectors. Very good. The elements inside U4 are in the format of 2 dimensions. Very good. They are conditioned by this equation. Remember, this equation was an equation of what? 2x minus y equal 1. If I take y in one side, this will make 2x minus 1 in the other side. Yes, it's like a straight line. It's a linear equation in the xy coordinate. So for every x element, there exists a corresponding y. Here, when x is 0, y is negative 1. Right? And when y is 0, x will be half. So these two straight lines, we can connect them, and hence we get that straight line. So this straight line is the y equal to x minus 1. It means that U4 includes all the points that lies in that straight line. All the points that lies over that straight line, of course, the number is infinite. And every point that lies in that straight line got an x coordinate and a corresponding y. This is why it's of 2 dimensions. So all the points that lies in this straight line are inside U4, and therefore it's a subset of R2. It includes some of the points that exist in R2, in all R2, in all the 2 dimensions. R2 has a point here and there and everywhere, right? So that line includes points only at that line. Now let's rigidly test the conditions. So the first thing, if x is equal y is equal 0, this means that we have the 0 vector. Now let's test the condition, that condition, which says that 2 times the first element was x, and here it's 0. So 2 times 0 minus the second element, which is 0. It was y there, and here it's 0. Does this equal to 1? 2 times 0 minus 0, this is 0. 0 is equal to 1? It's a false statement. And false statement means that what we were looking for does not exist. Now we were looking for the non-emptiness of that set. And if it's non-empty or not, reaching a false statement says that it's not. So it's not non-empty, and therefore we can conclude that U4 is what? it's not a subspace because the origin was not there. You might tell me, I have seen it from the description here that the origin is not there. I have just seen it. Why do I have to show it? Of course, we have to show it, okay? Although we have seen that the straight line doesn't pass by the origin, so it doesn't include the zero vector, we have to show it that it's non-empty. You can just mention that it's a non-empty. U4 is non-empty set, or it doesn't include the zero vector. You might say it in a different way. You can say that the zero vector does not belong to U4. Okay, this is solution number 2. You can say that 0 does not belong to U4 and therefore conclude directly that U4 is not a subspace. Okay, so it's as easy as that. Now let's take the other example in exercise 1, that one. I want you now, just by looking to that exercise, to tell me whether it's a subspace or not. Now you are able to do it. You will tell me, yeah, it includes the zero. The zero vector is there because it seems that we have here if x and y is 0. So this is for our discussion. You don't have to mention it. If x equal y equals 0, then 2 times 0 minus 0 is equal to 0 will give us a true statement. And therefore, the 0 vector does belong to U3. And therefore, U3 is non-empty set. Very good. Let's move to condition 2, the addition. In the addition, we need 2 elements. Let's call the first element U and take the characters, give them sub 1. And the second element, which is V, take the characters, give them sub 2. Now test the addition. U plus V. Take each 2 corresponding. So x1 plus x2. And then y1 plus y2. Very well. Now this is the shape of the elements of U3. Does this condition implies? Let's have a look. I will try to take 2 times the first element, which was here x1 plus x2, minus the second element, which is y1 plus y2, and enclose it by the brackets, equals 0. This was the condition here. 2 times the first component minus the second component equals 0. So I took here 2 times the first component minus the second component equals 0. Now let me rewrite it in a form such that 2 times x1 minus y1 plus 2 times x2 minus y2 equals 0. What about 2x1 minus y1? We have mentioned here that U does belong to U3, right? And if it belongs to U3, it means that this condition is fulfilled. That 2 times x1 minus y1 is equal to what here? To 0. So 2x1 minus y1 is 0. Also, we have to mention that V does belong to U3. Therefore, I can claim here that 2x2 minus y2 is 0. And 0 plus 0 is equal to 0. If I get a true statement anywhere, then what I was searching for was true. I was searching whether this sum vector, this resultant, belongs to U3 or not. And it seems that it's true. It does belong. And U3 is hence closed under addition. I think it's more clear now. I hope that it's more clear now. Now, number 3 is the third thing which we discussed. We prepare any constant which belongs to the set of ordinary numbers, and let's test whether C times U. Now I indicated that U belongs to U3 and C belongs to all numbers. So it's a scalar times vector. So it will look like this: C times x1 and C times y1. Now it looks like this vector, yes. Does this condition implied? Let me test. Does it belong to U3, this product? Let's test it. So we will test it. We will take 2 times the first component, which is cx1, minus the second component, which is cy1, equals 0. Let me take the c as a common factor so that we are left with 2x1 minus y1. Now 2x1 minus y1 is equal what? We said that u was belong to u3. So this x1 and y1 are conditioned with this condition. It's satisfied in the two components. So 2x1 minus y1 is 0. And 0 times anything times c is 0. Therefore, this statement is 0 equals 0, which is what? It's true. Then what I was looking for is also true. Therefore, u3 directly is closed under scalar multiplication, and we can conclude that therefore u3 is what? Is a subspace. Then u3 is a subspace because the three conditions are fulfilled. Okay, let's move to another exercise. Here, if we got that B, yeah, we didn't take B. So here B is u1, and this is the shape of the vectors, and this is the condition that lambda belongs to all real numbers. Let's go to the non-emptiness test and take the vectors 0 and 0. Now we have 1 0 plus lambda times 1 0, and we need this vector to be or to give the 0 vector. Is this possible? Now it's mentioned that lambda belongs to a set of all real numbers, so we might choose any value of lambda. Choosing the lambda by what? That will give us 0 and 0. We have here 1 and 0 and 1 and 0, so we need only a sign between them to produce the 0 vector. So let's denote that lambda with -1. Let's give lambda the value -1. So we will say that at lambda equals -1, the 0 vector will belong to the set u1, and therefore it's a non-empty set. Yes, it's non-empty. Let's move to the second. Here I need two elements. Let's take x, which is equal a vector, which is equal to 1 0 plus I will take the character and give it sub 1. So it's lambda 1 times 1 0. And now let's solve this. So it will be 1 plus this lambda 1 will be distributed. So you will have 1 plus lambda 1 in the first component, and the second component is kept by 0. So this element does belong to u1. This is what I'm telling him. It belongs to u1. This means that this lambda 1 belongs to the set of all real numbers. Okay, let's also get y, which will be directly 1 plus lambda 2 at that time, and 0, and it does belong to u2. You might write it in details like we did here, or directly. Now let's test the addition. Now we know what is x and y, so we can use them and take the addition, which will be 1 plus lambda 1 plus 1 plus lambda 2. This is adding the two corresponding elements, and 0. Right? Now we need this to look like that shape at u1 that was described here. So we might rewrite it simply, taking 1 and 0, and we will be left by what? We will be left by lambda 1 plus lambda 2 and 0. Right? This will be the rest. So we now separated the 1 and 0. Let's also continue to get the same format. So it's 1 and 0 plus, take all the common factor from the first component, because we need the first component to be only 1. So it will be lambda 1 plus lambda 2 plus 1. Of course, the addition is commute. I can change the order of the numbers. So it can be lambda 1 plus lambda 2 plus 1. and we will be left with 1 and 0, right? Now we have mentioned that lambda 1, which is part of X, it does belong to U1, so it does belong to the set of R. Very good. Lambda 2 as well. It means that lambda 1 plus lambda 2 plus 1, this sum belongs to the set of all real numbers. Yes, this is a scalar quantity that we can call it alpha. We can call it any other character, right? In order to get exactly the shape. Therefore, this shape does belong to U1. Okay, move to exercise property 3. We need a constant which we will indicate that it belongs to all real number. Now multiply C by one of the two elements, any one, X or Y. It will be what? It will be C times 1 plus lambda 1, and here C times 0. Again, we need this to look like something from the above. So we will have here C plus C times lambda 1 and 0, right? Okay, we need to set it in that form. So what are we going to do here? We are going to do a small trick. Let me remove that bracket. In order to add the needed trick, we need 1 and 0, right? So we might add 1 and subtract 1. By this, have we changed anything in the vector? We added 1 and subtracted 1. Because we seek to put it in that format of U1, which was described here. So now we have 1 in the first component, which we can isolate it or take it separately, 1 and 0. And take all the left from the elements of the first component in the other side with the 0. Now we have separated the 1 and 0, and we took all the left, which is C plus C lambda 1 minus 1. Okay, we need to rewrite it further to be 1 plus 0, and then we have this C plus C lambda 1 minus 1. All these values are scalars, right? Lambda 1 and C minus 1 are scalars, so we might call it alpha or anything, and we will be left with 1 and 0. Therefore, this trick make that resultant, this product, belongs to U1. And if it belongs to U1, then U1 is closed under scalar multiplication. And hence, we can conclude that U1 is what? Yes, is a subspace. Right? So therefore, U1 is a subspace. I will leave U5 because it's very trivial. You can do it. U5. So U5 will be a subspace, and you will be able to do it. Now let's move to the second concept, and before doing this, let's take some consequences for what we have just discussed about the subspaces. So if V is a vector in capital V is the set of all vectors. Okay, so V is an element. Very good. Then all scalar multiples of V are in V as well, all its scalar multiples by the third property of the scalar multiplication. In other words, the line through any non-zero vector is also contained in V. I will describe it in a better way. Do you remember at U node of this exercise, it was described like this, as lambda times 1 and 0. And the condition of lambda was that it belongs to the set of all real numbers. If we expanded this set, it will include what? Lambda now belongs to all real numbers, so it can be any value from the real numbers. And it's multiplied by the vector 1 and 0. So this vector might include 2 and 0. It might include negative 1 and 0. It might include any number in the x component, right, and 0. Which means that all multiples of the vector 1 and 0 exist in that infinite set, the set of infinite elements, right? Remember, the set of infinite elements, we call it what? The span set. Is vector x, for example. And in this case, this set includes all possible linear combinations of x. Linear combinations of one vector, we know that if we have a linear combination between two vectors, it will be ax plus by, for example. This is a linear combination between x and y, because it's any constant times x plus any other constant times y equals 0. So this is a linear combination between two vectors. If I wanted for one vector, they said take one term. If you wanted only for x, take that only term of x. So any constant times the vector x, like we have here, a constant times the vector x. So this set is all possible multiples of the vector x, and hence we can call it the span of x. If you just figured out that it's a span set, the given set U node is a span set, this is U node, you can directly conclude that then U node is a subspace. Why? Why? Without the three conditions? Yes, without the three conditions. This is because every subspace is a span set, and every span set is a subspace. This is a very good note that might save a lot of effort. If we have figured out that we are speaking about all possible linear combinations, I want you to figure out also the exercise that I left you for your exercise, that part 5 here. It's a constant times a vector plus another constant times another vector. These two constants are free, they can be any number. So we are talking here about a linear combination between these two vectors. So U5 spans x1 and x2, or U and V, these two vectors. And if it spans these two vectors, we can directly conclude that it is a subspace. Why? Because of this theorem, which says that spans are subspaces and subspaces are spans. Okay. So a subspace contains the span of any vector. The span of any vector. And therefore, all of the spans U and V will be contained in V. We don't have to take these consequences in details. I'm just giving you what we need and what is important. If we have a set Rn, which means that it's a set of infinite number of vectors, is a subspace of itself. So, is every subspace a subspace of itself? Yes. Every subspace is a subspace of itself. Indeed, it contains the zero vector, it's non-empty, and closed under addition and scalar multiplication. Okay, the set 0 that contains only 0 vector, we call it a subspace of any Rn. For example, if we have a set, let's discuss it in R2 or in R3. So if we have the set that includes the 0 vector that belongs to R3, thus this set is a subspace. Is it a subspace of R3? Now we have taken a set that contains only the 0 vector and it's a subset of Rn. We will say that yes, this set that includes only the 0 vector is a subspace of R3. It contains the 0, and if you added 0 to itself or multiply 0 by a scalar, it will give you the same vector which is included in the set. Therefore, the three conditions are applied. It's something trivial, but it's a theoretical part. Okay. Now we have subsets versus subspaces. So we said that the subset is any collection of vectors whatsoever, like here in the unit circle. This unit circle includes some points that are existing in R2, the points that lies in the circumference of the circle, right? They are a subset of the points that exist in R2. Hence, it's not a subspace. Why? Because this equation of the circle doesn't include the origin. The origin is not a point in the circle circumference, right? So if we set x by 0 and y by 0, it will be 0 equals 1, which is a false statement. This is just to give you different views. Now here we need to discuss the linear dependency and independency. The definition of the linear dependency and independency, let's take it here. Now this is concept number 2 about the linear dependency. And I will tell you that the linear dependency is the same as the linear combination. It's very simple concept. Linear combination and linear dependency means that there are elements that depends in each other linearly. So we can call that A times U plus B times V plus C times X, for example, plus D times Y is equal to 0. If this linear relationship exists, it's linear. Why? Because the unknowns A, B, C, D are of powers 1, right? And they've got coefficients which are numbers. The U, V, X, and Y will be vectors that are given. And we need to test whether the U, the V, the X, and the Y are linearly dependent or linearly independent. We always test the linear independency. So we always test the linear independency. But I want to start from the linear dependency because we have just taken the linear combination. And we know that this relation means that there is, if it's true, if it has a solution, if it has a single solution at least, and if at least one of these A, B, C, D multiples is not equal to 0. So at least A or B or C or D is not equal to 0, and there exists a solution. There exists a solution for that system. Therefore, we will say that there exists linear dependency between U, V, X, and Y and linear combination. But we need now to know the linear independency, which is the opposite of linear dependency. If they do not rely in each other in a linear relationship, this means that we need the case where this relation does not exist. And this will be the case when A will be equal to B equals C equals D equals 0. If you remember, if we set here the values of U, values of V, values of X, values of Y, and the equal in the matrix form was the bar, and we have the 0 vector, and we set the matrix form. Solving the system with zeros in the right side means that we are dealing with homogeneous or inhomogeneous system of linear equations. Homogeneous linear system of equations, right? When the right side is 0. And that type of systems had how many solutions? It had unique solution and infinite, right? The unique, we called it trivial solution, which was zeros. It was only 0. So all of A, B, C were equal, or the solution was zeros. All the unknowns we are looking for were zeros. And the other option, which is the infinite solution, they called it the non-trivial, and it holds the parameter representation where we call we have something plus another vector times t or times r, such that this t belongs to the set of all real numbers. You remember this representation of the solution? if we are solving for a, b, c, for example, so it will be a vector plus another vector times t, such that t belongs to all real numbers, and hence we have infinite number of solutions. That was the homogeneous system. And if I'm telling you that we need the solution to be equal to the zero vector, it seems that we need that trivial solution. So we will start by this relationship. This is the relationship we are looking for, whether it exists or not. If the vectors are linearly dependent, then this relationship exists. If this relationship does not exist and all of the constants are equal to 0, this means that 0 is equal to 0, there's no relationship. Then the vectors are linearly independent. In other words, if at least one of the a, b, c, d is not equal to 0, we will say that there is a relation and there is a linear combination between them and linear dependency. Let's go quickly to the problems. This is just recalling from the lecture what you have did. And now we need to solve. Let's take number A. So this is an exercise 2, which says that for each of the following group of vectors, decide whether the vectors are linearly independent or linearly dependent. So we will start by assuming that there exists linear relationship. Okay. Now this is our assumption. This is the linear dependency relationship that we assume. Let's set the known and the unknown. Of course, we know that the known is the u vector, so we will put it 1, 1, 2. The v vector is also given. The w vector is also given. Now the equal is what? It's the bar of zeros. And we need to solve this system for the unknowns, which are a, b, and c. Let's reduce this system using the elementary row operations. And of course now we know how to do it. So let's skip that part. I will get you the reduced form directly, which will give us 1, 0, 0, 0, 1, 0, 1, 0, 0 of zeros. Now this form is the echelon or the reduced. Of course, you will trace by your eyes the main diagonal elements, and you will find that it's eliminated. The upper and the lower triangle elements are eliminated. So this is the reduced form. This is the reduced echelon form. Very good. So we can directly read the unknowns. The unknowns were a, b, c, and that was the equal. So from the last row, a is eliminated, b is eliminated. So the last row says that c is equal to 0. And the second row says that b is equal to 0. And the first row says that a is equal to 0. And hence we have what? The trivial solution. Right? And therefore, u, v, and w are linearly independent. Therefore, this linear combination does not exist. This linear dependency does not exist. Then the vectors are linearly independent, right? So they are linearly dependent or linearly independent. If they are not linearly dependent, then they are linearly independent. Let's take that exercise here. So we have these three vectors, x, y, and z, and we need to test whether they are linearly dependent or not. If we are testing whether they are linearly independent or not, so I will assume a linear relationship. I will take a, any constant times x, plus b, any constant times y, plus c, any constant times z, and I will be looking for the values of a, b, and c. So let's put the known values. X, y is 6, 0, 4, z is 2, 3, 1 equal is the bar, zeros. Very good. Let's reduce this system to reach its echelon form. You don't have to get its reduced echelon form, by the way. This is an extra effort. We don't have problem in the back substitution, so you might get the echelon form and apply the back substitution to read the solution. Here, this is the reduced echelon form. You remember the case where we have zero vector at the end. If we have zero vector that popped up in any of the rows, we push it to the bottom, right? So if we have zero vector in the bottom, this says what? Let's trace the main diagonal elements. This says that we have here a free term. This is not a pivot. This column was for A coefficients of B, and that one for the coefficients of C equal, right? So it seems that C doesn't have a pivot, so it's a free parameter for that system. It doesn't contribute in its solution nor behavior. And therefore, we will be asked to write A and B in terms or with respect to that C, and mention that the C is a free parameter. You might say that C is equal to T or R or C, as it is, and C belongs to all real numbers. You don't have to write this. I'm just writing it for extra, for illustration, for our discussion purpose. So row 3 is very important, and it tells us that 0 is equal to 0, which is a true statement. Row 2 will tell us that A is eliminated. Let's read row 2. B is with us, plus C equals 0. Very good. And row 1, go up to row 1. A is with us, minus C is equal to 0. If C is the free term, then we have to write every other unknown with respect to it. So I can write here that B is negative C and that A is equal to C. And therefore the vector of unknowns A, B, C is what? A is equal to C, so it's 1 times C. B is negative C, so it's negative 1 times C, and C is equal C. This is why I wrote here that C is equal to C, in order to see that its coefficient is 1, not 0. Some of you do it. So it is 1. And we have to mention beside that C belongs to all real numbers, and therefore for every possible value of C, there exists an equivalent combination of A, B, C. So we don't have here a single linear combination or a single linear dependency. There is infinite number of possibilities. There is infinite number of combinations between A, B, and C that make this statement true. And therefore, it exists and there is linear dependency. So we will just say that this set is not linearly independent. And always in your negation, use not. Instead of telling yourself linear independency, its negation is linear dependency. Also, the non-empty set that we mentioned in the subspace, its negation is the empty set. No, in math, they just use the not. For many reasons, which we don't have to discuss now. So we just use not non-empty set if I need to negate it. If I need to negate here the linear independency, I will use not linear independent. Okay? Just as simple as that. Now we need to move. I will leave for you part B and D in the worksheet. And of course, revise and check your solution, your final solution with the solution file. Here we have in part B, I just want to give you a note that the first component is non-zero and the second is 0. Here they are the opposite. The second is 0 and this is non-zero. The third, this is non-zero and 0. The fourth, this is 0 and non-zero. In such a situation, they are directly linear independent, because there is nothing that I can multiply by this lambda that gives us 0 except 0. And here there is nothing that I can multiply by this, it's not lambda, so it's pi. By this pi, which is 3.14, it's a number, of course, you all know it. There is no number that I can multiply by this pi that delivers 0 except 0. So it's A plus that vector plus B times that vector in order to give us 0 This means that A and B are zeros. And it implies that X and Y are linearly independent just by looking to the two vectors. Okay, just for yourself. And of course, if you are solving it, you have to show it. Here, we will correct that this one is 0 in X3, this one is 0. You will find the updated version of worksheet 5. Please take a look over it in the CMS. Now we need to move to the third thing here, and before moving to it, let's see if we have any notes here. Yes. Now we have the set of vectors. These vectors in V, they are linearly independent only if the scalars R1 through Rk are equal to 0, right? So we have the trivial solution, and we will hence conclude that these vectors x1 through xk is not linearly dependent, which means that there is no dependency among each other linearly, so they are linearly independent. Now, if these vectors are linearly independent, then it is not possible to write any of the vectors with respect to the others in a linear combination or a linear relation. I might take x1 here and put it on the other side and divide all the R2 through Rk by R1, right? Because they are constants and numbers. And this will deliver x1 as a linear combination of the other. In order to be linearly independent, it means that none of the vectors can be written as a linear combination of the others. This is just emphasizing the idea. Now, if we have a set of one vector, it means that it's a linear independent. This set is linearly independent because it's including only one vector. So with no doubt, it's linear independent. Also, if we have such two vectors, every corresponding elements, one of them is 0. So the first elements, one of them is 0. The second elements, one of them is 0. Then this set is linearly independent subset of R2. Here, this set includes 3 vectors. These 3 vectors, every corresponding elements include only one non-zero. Here 2 zeros and 1 non-zero. The second 2 zeros, 1 non-zero. The first 1 non-zero and 2 zeros. Therefore, this set is linearly independent. Also for R4 and so on. Here for Rn of n components, if it exists that only one non-zero in every corresponding element, then it's linearly independent. Also, the 1 is a linear independent of the polynomials of order 0, because polynomials of order 0 includes only a number, like y equal 2, y equal 3. This is a different thing, and we don't have such examples in the worksheet, so let's skip it. Here, if we have x1, x2, x3, and x4, and we need to see whether this set of vectors is linearly dependent or independent, we directly put the vectors in columns and solve the system or reduce it, and we need to see the type of solution. So if we have here the 0 vector at the end, and we were solving for 4 unknowns, right? Because they are 4 vectors. So here is, for example, A, B, C, and D. This tells us that it's not an augmented matrix, it's a matrix of coefficients. Because, you know, in the homogeneous system, when the right side is only zeros, we might work in the matrix of coefficients only, because we know that all of the right side is zeros. So this means that we have a 0 vector at the end, and it implies an infinite number of solutions, and therefore these vectors are linearly dependent. Okay, so this is a shortcut that shows you might just apply the answer like this. Okay, the linear dependency geometrically also in the 2D and 3D, if the two vectors are linearly dependent, it means that they are collinear, or like here, like it's indicated here, that these two vectors are collinear, so they exist in the same straight line. If we extended a straight line passing by the two vectors, they will be in the same line, and this means that they are collinear. This is geometrically. It's always geometrically is always only for your better understanding and sensing of the concept. Okay, here for the 3D vectors, the 3 linear independent vector the three linear dependent vector will be coplanar, so they will exist in the same plane. If we extended that plane to the dimensions, the other dimensions, there it will include the vectors, and if the vectors are in the same plane, it means that they are linearly dependent. If they are in the same line, then they are dependent. Okay, let's move to the third concept and last one for this tutorial. It's the basis set, the basis and dimensions. What is the basis set? Unlike the other sets that we have just discussed, the basis set, which is denoted by capital B, it will be a finite number of, it's a finite set that includes finite number of elements, okay? Such that what? These elements can span finite set that spans another set. And the elements of this set that we have just discussed got to be linearly independent, and they got to span this Rn, like we will see in the examples now. There is a third implication for these two conditions, that we have to have n tuples elements. It has to include n tuple element. Let me make this statement or this theorem more clear through an example. Let's take the example for R2. If we need to set the basis set of R2, it will be a set of these two vectors, 1, 0, 0, 1. Why these two vectors? Because for R2, the n here is equal to 2. So we need two tuples vectors. Two vectors, each of two tuples or two components. If you remember from tutorial 1, we said that the elements here might be called components, entities, elements, or tuples. So we have here two vectors, each is of two tuples. This first one is filtering the x component, and this is filtering the y component. The span of these two vectors, the span of the basis vector, is equal to R2. So we need the least number of vectors that can span a set, an infinite space, or any given set. Okay, in other words, R2 will be equal to all possible linear combinations of 1, 0 and 0, 1. It all makes sense. Okay, the dimension of B will be the number of elements in B, which means that in order to get the dimension, we have to get the basis set at the beginning. Here the dimension is equal to what? In that B set, we have two elements, so the dimension is 2, right? Does R2 has only one basis set? This basis set is called, for example, the basic basis. Basis with an I is the singular, with E is the plural. So this is the basic basis set, which means that sometimes it's called the Euclidean, okay? The Euclidean basis, which means that there exist other basis sets. We can find more basis sets, but each base set for R2 will be of two vectors, each belongs to R2, okay? If the two vectors are linearly independent and can span R2, we will call them directly basis set. They can act as a basis set for R2. So R2 doesn't imply that it's only including these, this set. Let's take R3 as an example as well. If I want to get a basis set for R3, I will call it B1. This set will include what? Actually, it will include 1, 0, 0. and 0 1 0 and 0 0 1. This will be the elements, okay? And again, it's the basic set of R3. So if we studied the span of these three vectors, they will generate the whole R3. And the dimension of B1 at that time is what? 3. By the way, for the dimension of the basis set, for the dimension, of course, by logic, you have to find the basis set, and number 2, you will count the elements. You will count the elements of that B. And there is a shortcut, or you might only get the rank. You might get the rank. Do you remember the rank? The rank is after reaching the row echelon form, we count the number of non-zero rows. So that was proven, and it got a theorem that states it. Don't worry, you may use it directly for getting the dimension, and it will decrease the effort and everything. Let's take exercise now from the worksheet. Here, let's take exercise 4. I would like to take all of exercise 4 and discuss it with you. So here it says, so now dears, in exercise 4, we recall that the basis set is a set such that its elements are linearly independent and they can span a certain Rn, and the first check is that they are n-tuple elements that we might call that they span Rn, okay, and they are n vectors. So first we check that they are n of n tuples, and then we check the linear independency, and finally we check the span set if both agrees. Okay, if they were n tuple elements, then we will check linear independency, then the span set. If they are not from the beginning n tuple elements, then we will not check any, and we will say that they are not basis set. Let's try here in number A. Number A, we have 3 elements that belongs to, I wanted to start exercise 4, not this exercise. There's another one before it. Yes, exercise 3 first. So let's take exercise 3 first, and then we will continue with exercise 4, and you will find it's very similar, but I need the ideas here. So which of the following sets is a vector, is vectors form bases of R2? Form bases of R2. We know the example that we discussed is the bases of R2. These are the standard bases of R2, only the standard, and we might have infinite number of bases for R2. So can this set work as a basis set for R2? Does it include linear independent vectors and it spans R2? Of course, the first check, which is of n tuple elements, does not succeed. So they are of less number. So it will not, it's not B, because the basis set we will call it B. So it's a not basis set of R2. And why? We will say because it's it can't span R2. Okay, the second example, we have here 3 vectors. Can this set act as a basis set for R2? We will go here to check number 1. n tuple elements? No, they are 3 components. Then we will say it's not P, and we will mention the reason that they are not linearly independent. They are not linearly independent. Why? We can observe here that this vector in the middle, which is 1 and 2, is equal to the first vector, which is 1, 0, plus 2 times the third vector, which is 0, 1, right? So this is a linear dependency. Now the three vectors, if their number exceeded that required n, for R2 here n is 2, if the number exceeded that 2, then they will be definitely not linearly independent. Okay, there exists one which is redundant, so they will be not linearly independent. If their number is less, here the number was bigger than 2. If the number is less than 2, the number of elements, then they will not be able to span, because the span set of such a vector is all the multiples of this vector, which can get all the vectors in R2 with y coordinate 0, with the second component set to 0. So you will not be able to reach all vectors in R2, and hence it can't span R2. Okay, we just indicated. What about number I? They are two vectors and each belongs to R2. Very good. This condition is, they passed that third condition. Let's go to the linear independency. We will notice that the first vector is double of the second vector, just by noticing that this is a linear dependency. So they are not linearly independent. And that's it. They are not linearly independent, and that's it. Okay, what about the last one? They are two, and we cannot notice any linear dependency between them, right? So we have to check. We have to set the check of linear independency. We cannot say that we don't observe any linear dependency in between the two vectors, therefore they are linearly independent. No, we have to show it. So first, let's discuss the linear independency, which says we need A times the first vector. You can call it U and V, or you can keep it like this, plus B times the second vector equal to 0, 0. This is the linear independency check. And now we will work in the system. Let's work in the system. So we will take negative 2 and 3, and we will take 1 and 2 of zeros and reduce the system. By reducing it, we will reach that reduced echelon form. You may only reduce it to the echelon form, and hence you can directly read the results, which is it was A and B, the unknowns, equal. So it seems that A and B, this vector of unknown, is the 0 vector, right? And hence we have the trivial solution. And the trivial solution for the linear independency means that they are linearly independent. Okay, let's check now the span, because if they are linearly independent, does it mean that they will span R2? And if they span R2, doesn't mean that they are linearly independent. The span test will be again like the linear independency, but at that time we need to test whether the linear combination of these vectors gives an infinite solution or not. We need this linear combination to construct or format every vector in R2, right? We need this to act as the span of these two vectors, or the linear combination between two vectors, get infinite number of solution and construct all of the vectors in R2. Therefore, we solve for free solution. Please notice what happened here. So for the linear independency, we set the 0 here. For the span, we set the x and y. Okay, this is the only difference. It comes from the concept itself, of course. So if we have here A times the vector x plus B times the vector y, this is equal to 0. This is that we check for the linear independency. Okay, what about the span? The span, we will say A times x plus B times y, but equal to another vector V that's written or expanded as x and y. You might use, of course, different labels if you will mix it up, but don't worry, it's the same idea, right? Okay, so now let's go further in solving that system in that way. I will take that system, this will take some space. It's very simple how we will solve it, but please watch it out. I will construct the augmented matrix, which is negative 2, 3, 1 and 2 of what this time? Of x and y, not 0 and 0, right? Now I need to reduce it. So I will multiply row 1 by negative half. I know now you know it. So I will make it just direct. I just want to show you that the x and y will be included in the operations. Multiplying by negative half. This will keep that 3 and that 2 and this is y. Very good. Now I need to eliminate this 3 using that one. It's a good revision as well. So I will multiply row 1 by negative 3 and add it to row 2. Right? And this means that row 1 is of no change. So I will write it as it is. And row 1 will be multiplied here instead of row 2 because this operation will be updating the row 2. I will multiply row 1 by negative 3. So this will be negative 3. And negative 3 times 0 is 0. And negative 3 times this will give us 3x over 2. Now I will directly add this values that we have commuted, which is negative 3 times r1 by row 2. 3 plus negative 3, that is 0. 0 plus 2, this is 2. And 3x over 2 plus y, it will be 3 over 2x plus y. So this is what's left. Okay, now I need this 2 to be what? Why this 1 here, this 1 came here to be 0? It's not 0. This one should be, and in that case this will change as well. So here this 1 times negative half, it will be negative half. I will write it with the red or that color. So it's 1 times negative half because from here to there we multiplied row 1 by negative half. And then multiply row 1 by negative 3. I'm sorry for this. I don't know how I mixed up. Row 1 times negative 3. So this will be 3 over 2. Adding this 3 over 2 to row 2, 3 over 2 plus 2. So this will be 4 over 2. So you will have here 7 over 2. Right? And this will be kept as it is, negative half. It will be kept as it is row 1. And row 2 is the updated one. Now we need to set this element into 1. So I will get back the white color. And I will multiply row 2 over 7. And there we will have the first row without change. And the second row multiplied by 2 over 7. This will be 1. And this will be the 2 will go with the 2. And we will get 3 over 7 x plus 1 over 7 y. Right? And finally we need to eliminate that element, or this is echelon form. We might solve it using back substitution, but I will use the elementary row operation to get the reduced form better. So I will multiply row 2 with half and add it into row 1. This means that row 2 will be of no change. It will have the 3 over 7x plus 1 over 7y, right? And row 1 will be the changed one. It will be 1 and 0. And here we will have half row 2. So this needs to be multiplied by half. It will be 3 over 14x plus 1 over 14y. We need to add half row 2 into row 1. So it means that we will add the negative x over 2. And therefore we will get 1 over 14y, yes. And the x will be this to be over 14. It will be 7 over 14. 3 minus 7 is negative 4 over 14 y, which can be written as 2 over 7. So I will write it here, 1 over 14 y minus 2 over 7 x. This one is x. Okay. I'm sorry for that. Maybe this is from fasting or something. So So I need here to set this as minus 2 over 7x, and here we reduce that system. We might go back to remember the unknowns that we were solving for. We were solving for a and b as usual for that part. So this is a and b, and that is the equal. So I can read the solution as a equals to 1 over 14y minus 2 over 7x, and b will be equal to 3 over 7x plus 1 over 7y. And we will say that for all right hand side, these solutions or these values are true. They are true for all right hand side, because x and y here that we used were belonging to all real numbers. This vector that is v, this v was belong to all real numbers. If it belongs to R2, it means that each of the components belongs to R. So here x and y are free, so you might find infinite numbers of a and b that we write. We might write it as we are used to the vector of unknowns a and b is equal to something multiplied by x, which is a free parameter, plus something multiplied by y. So what is multiplied by x? Here I have negative 2 over 7, and here it's 3 over 7. You might write it negative 2 and 3. You might multiply it by 7 because x is any parameter, so we might multiply this x by 1 over 7, and the new x is x over 7. It's okay. Here the y will be 1 over 14 at a and 1 over 7 with b. So this is the final solution, and we should indicate that x and y belongs to the set of all real numbers. And that's it. So finally, for the dimension, that's it for that exercise. You might discuss also exercise 4. I will keep it for you. Of course, here the number is less than 3 because we need to test if it's n tuple vectors, then it can't span. Here they are 3, so we will test the linear independency. Here we have only one non-zero in the third component. We have two non-zeros in the second and two non-zeros in the third, so you have to check the linear independency. Here in the number C, this number, the square root of negative 1, although they are linearly independent and they can span R3, but we will say that they will not be able to span R3 because this value is not real number. And R3 includes real number. If they were 1, as you can figure out, they will turn to be the bases of the basic bases of R3 or the Euclidean, right? Okay, in exercise 5, we need to get the dimension of some of the vectors. I will take that. Now determine the dimension of each of the following subspaces, and here U3 is the span of these two vectors. So U3 includes all the possible linear combinations of these two vectors, right? And linear combination means that we have A times the first vector plus B times the second vector. If I call that U and that is V, right? It will be equal to what? To U3. To the set U3. It's all possible linear combinations. This is the description of the span set. Okay, if I need to get only the dimension, it means that these two vectors can act as bases for that U3? We will find out, because the basis has to have the same dimension. Now their number is 2, and each of them belongs to the R3. So they are not definitely bases of R3, right? They are not bases of R3, because if they are bases of R3, they got to be of 3 vectors since each belongs to R3, right? So it makes sense. Now I will check for the linear independency. It seems that U3 is a subset of R3. Okay, so I will check the linear independency, because they got to be bases. The linear independency, you will do the test a times u plus b times v equals 0, replacing 1, 3, negative 1, and 2, 1, and 0 of zeros. This is the homogeneous system. Solving it, we will find that a is equal to 0 and b is equal to 0, and hence it's the trivial solution, which means that they are linearly independent. If they are linearly independent, then, and they are spanning U3, and they span U3, therefore they act as the basis of what? Of U3. And the dimension of U3 basis, of the basis set of U3, will be what? Equal to their number, which is 2. Okay, we can go to the other exercise. So here the dimension of U3 is 2. This was number A that we solved. And this implies that U3 is not R3. It's a subset of R3. Okay, emphasize this information. Here we have 3 vectors. So we have to find if they are linearly independent, because U4 here we have three tuples vectors. So they might act as basis for R3. We have to check the linear independency first. And we are going to find that the 3 vectors are independent, and therefore they are spanning the U4, and therefore their dimension is equal to 3. Okay, these are the bases of U4, of the U4 mentioned here, and the dimension is equal to 3. Here the required is only the dimension. Okay, but if the dimension is equal to 3, it implies that U4 is R3. Right? This implies that this U4 is R3, because these act as basis for U4, which is for 3 of 3 tuples vectors. Okay, here in number C, we have 3 vectors, and both each of them belongs to R3. Okay, so we suspect that this U5 would be R3 as well. So we have to check first the linear independency, because we need to check whether they are bases or not. So we check the linear independency, and we will find that they are independent. The only 2 vectors that are linearly independent, and this means that their dimension is equal to 2. How do we know the linear independent? I will tell you here. If we traced this, so tracing that, I'm sorry, I need a pen if it's possible. Okay, so if we have here, if we can trace this linear, if we can trace this main diagonal element, I will take this exercise to here. Okay, so if we have this, let me trace here the main diagonal elements. We find that there is a pivot here and a pivot there, and the pivots indicate the linear independent vectors. So here the first vector is linearly independent with the second, while the third doesn't have a pivot. It has a free term, so it's a dependent vector. So we see here, we see here that the number of pivots are 2, only 2 pivots or leading coefficients, and therefore we have only 2 vectors that are independent. Therefore the dimension is equal to 2, because only 2 were linearly independent, and we said that this set already spans U5. So we have only the 2 vectors, this first and the third, and hence U5 is not R3. because the dimension of its basis set is not equal to 3 like R3. The dimension of U5 basis set is 2. You might also try to get the echelon form. So as another solution, here I might write these vectors because they are here already. They are here and there, they are the same. So I might reduce this system to get its form. Okay, and its rank will be equal to the dimension. So I will decrease it. So here, after reducing this system, this is of course the echelon form. Tracing the main diagonal elements, the lower triangle elements are eliminated, so that is echelon form, and hence we can deduce the rank. We have here a 0 vector, so it's not counted. We count the non-zero vectors, which are equal to 2. So also the rank can get us the dimension, and I can say that hence the dimension of it was called U what? This U was U5. So the dimension of U5 is equal to 2. Okay. Finally, here, if we move into part D, we have to find the number of linearly independent vectors. They are 4 vectors, each belongs to R4. So they are linearly independent. We have only 2 linear independent vectors by reducing the system, and hence the dimension is 2, and this U6 is not the R4, right? Also, it's obvious that the first vector, which is 1, 2, 3, 4, and vector number 3, their sum gets the vector number 5. So it seems that they are not linearly independent, right? Therefore, the given 4 vectors are reduced to the first and third vectors only, which are linearly independent, and hence these 2 vectors only, this is the least number of vectors that can span U6, and both are linearly independent. So the conditions are applied so they can act as basis for U6, and this makes the dimension of U6 equals to 2, right? That was the end of that tutorial. Thank you very much for your attention. See you next time. Bye bye.